Let's look at the integrated rate law and a graphical method of determining the reaction order. A rate law shows how the rate of reaction depends on concentration, and it uses initial concentrations. But we are more interested in how concentrations with time, and so we use what's called the integrated rate law. And on your AP data sheet, they list these integrated rate laws. The very first one, that is for zero order reactions. The second one is the first order reactions, then second order reactions. And then it addresses half-life, and half-life is always a first order reaction. So if it mentions anything about half-life, see if you can't use this half-life equation. Let's first look at a zero order reaction. So I can list my rate law as rate is equal to the rate law constant. Let's look at the integrated rate law, which this says that the concentration at some sort of time, or the final concentration, minus the initial concentration will be equal to the rate law constant times that time. In a zero order reaction, if we graph concentration versus time, we are going to get a straight line. If you are to graph the natural log of the concentration versus time, or 1 over the concentration versus time, you're always going to get a curved line. So you can tell from the graph you have a zero order reaction. And again, you'll have a straight line for concentration versus time. Let's do a zero order reaction problem. A lot of times the AP board just goes ahead and tells you what order reaction it is. However, you could figure out the order of reaction from the units that are on that K, that rate law constant, or maybe they give you a data table for you to figure out if it's a zero order reaction. Remember, in a zero order reaction, the concentration can change and the rate stays the same. So in this problem, we have ammonia decomposing on a tungsten plate to yield nitrogen and hydrogen. And there is a balancing equation, but remember with rates, the coefficients of balancing the equation have nothing to do with the rate law. We can find K by finding the negative slope. And again, this is a zero order reaction, so we would expect there to be a straight line if the concentration is graphed against the time. So let's first find the K by finding the negative slope. To find the slope, I've always been taught rise over run, or the final minus the initial concentration divided by the final minus initial time. And looking at the graph, I can see that this right here, that is about 2.8 times 10 to the minus 3 molar concentration, and I'm just going to go all the way to the end right here. That's about right in the middle, so that's 1.5 times 10 to the minus 3. And so over time, that would be 1,000 seconds because my time is in seconds. Doing my math, I have a negative 1.3 times 10 to the minus 6 molarity per second. So that's what my K is. All right, let's do number 2. If the initial concentration of ammonia is that 0.028, that's the same thing as 2.8 times 10 to the minus 3 that I used before. At what time will the concentration be 0.0001 molar concentration? So I'm going to use the integrated rate law for a zero order reaction. So I just wrote my reaction. I'm going to solve for T, and then I'm going to put in my numbers. So my concentrations divided by that rate law constant that I just found. And my final answer, I get 2,077 seconds, or if you divide by 60, I would get 35 minutes is my answer. So in this problem, we used a graph to help us to find our concentrations, and so we could also find that rate law constant by finding the negative slope. Let's now look at the integrated rate law for a first order reaction. So on the AP data sheet, here is that formula. If you multiply through by a negative and combine your natural logs, you actually can rearrange it to look something like this. It does make it so that there's not as many negatives and so there's less error. I find that I tend to make a lot of errors with negatives. So you really have to pay attention to the negatives when you're doing these problems and write out each step so that you don't miss anything. When you graph a first order reaction, you get a straight line if you graph the natural log of the concentration versus time. So this is your straight line. And if I see that the natural log of the concentration versus time is straight, then I know it's a first order reaction. I'm going to get curved lines for just plain concentration versus time and for 1 over concentration versus time. Let's go ahead and do a first order reaction. So this says the reaction 2A yielding B is a first order in A with a rate constant of 2.8 times 10 to the minus 2 at a certain temperature, and that temperature is not important. As long as it stays the same temperature, then your rate log constant stays the same. How long will it take for A to decrease from 0.88 to 0.14? And you can use either one of these formulas. I'm going to go ahead and just use the first one because that's the one on your data sheet. Remember, this is going to be the second one that they give you because the second one is the first order reaction. So it's asking how long, so that's time. So I'm going to solve for t, and I'm going to rearrange my equation so that I have t is equal to the natural log of the concentration of your ending time minus the natural log of your initial concentration divided by the negative of the rate log constant. Let's go ahead and add our numbers. Generally, the concentration goes down, so your initial concentration, it should be higher than your ending concentration. So that's putting in all my values. Let's go ahead and take the natural log of those numbers. And I get a negative times a negative, 66 seconds. So multiplying through, I get 66 seconds. So that's the time that it will take to go from 0.88 molarity to 0.14 molarity. Looking at this graph, I can tell it's a first order reaction. And again, that's because it's the natural log of the concentration versus time, and it looks to be a straight line. Again, you can use the modified equation. I'm just going to use the one from the AP data sheet. So in this problem, this says the rate log constant, it's given to us. It's right there. That's what K is. And it says a first order reaction. So just flat out tells me. So I'm going to go to my data sheet and use the second one because that's the second order reaction formula. And here it is. And it says, what is the concentration of the N2O5 after 4 minutes? So that means I'm going to be solving for this. This is what I don't know. So I'm going to rearrange my equation to solve for that. Let me go ahead and put my numbers in there. So initial concentration, 0.16. Go ahead and take the natural log of that number. Okay, so I have the natural log of my ending concentration is equal to a negative 3.23. How do I get rid of that natural log? Well, you're going to use your E button. So you're going to take the E of both. So by doing this, I will have just the concentration, and I'll have e to the minus 3.23. And my concentration will be 0.04 molarity. Let's do another one for practice. Again, it tells me it's a first order reaction. There is my rate log constant. That's what K is. And it says, what is the time required? So I'm going to solve for T. Here's my formula. Put T on one side. I get the natural log of the ending concentration minus the natural log of the the initial, divided by the negative rate law constant. Let's put our numbers in. Let's go ahead and take the natural log of those numbers. Watch all the negative signs. And my final answer, I will get 1.3 minutes. So let's do one that has half-life in it. So again, it's the same reaction. N2O5 decomposes. It's a first-order reaction, and there's my rate law. What is the time for half of the sample to decay? So if I have my half-life, that is equal to the natural log of 2 divided by k. And the formula that they have there, they already take that natural log of 2. That is equal to 0.0693. So that's where they get it from. But really, all I need to do is I need to just put that half-life constant in there, and that will tell me my half-life. Your half-life is always a time. So my final answer, I get 1.98 minutes. So I have minutes in the denominator of a denominator, so that brings it up to the numerator. And if I look at sig figs, I get 2.0 minutes. Let's look at a graph of half-life. So the law of conservation of mass says that reactants become products. So in half-life, these reactants aren't disappearing, they're just becoming something else. They're becoming a product. And this also applies to nuclear decay. Nuclear decay is not part of the AP program, but it follows the same thing. So we can have either a reaction where the reactants are becoming products, or we can have, say, a radioactive isotope and it is becoming something else, something more stable. But looking at this, you can see that we have the concentration on the y-axis, the time on the x-axis. To find that half-life, you take whatever starting concentration you have, and then you just go to where you have half of it. So that's why this says concentration divided by 2. And then the half-life is always a time. So you would read at that half point and read what the time is. So if my time was in minutes, the half-life for this particular reaction would be 1 minute. So at 1 minute, half of the reactants have now become products. If you take and go another half-life, so you'd have 1/4, then you would just take that half-life of 1 and add another 1. That would give you 2. So at 2 minutes, I would have 1/4 of, or 25% of the reactant. And you could even take it one more time. So I would just add 1 more. So go to 3, and then that would be 1/8 of my original concentration. And half-life is always a first order reaction. The definition of half-life is the time required for half the sample to decay or to react. When we're looking at radioactive isotopes, each atom has a particular or unique half-life, and they actually use half-life to tell how radioactive it is. So if you have something that has a very short half-life, then that's very, very reactive. If you have something that is a longer half-life, then it's not as reactive. Let's look at this graph here. You can graphically determine, again, what the half-life is. So just find whatever the total your sample is. This one is 100%, and I would just go to 50%. And again, half-life is always a time. And so this one happens to have a time of 30 years. So not very reactive because it takes 30 years for half of it to become a product. Here's some example half-lives. So we have one that has 1.2 minutes, so that's very, very reactive. Uranium-238, it has a half-life of billions of years, so not very reactive. As far as nuclear decay, the nuclear decay is constant, but it's random. It doesn't happen all at once, and remember that things don't disappear, they just become a product. There is a way to do a little chart to find the half-life, or to use half-life to figure out how much you have left. And so we can set up number of half-lives here, and then we'll do time, and amount. The biggest thing that you should know as far as using this little chart is you always want to start off with a time of 0 or a time where there's no half-lives. And then my amount in this case is 100 grams. So before anything starts. So make sure you have a starting line. And then one half-life will go by, and it says it has a half-life of 10 years. So that means 10 years go by. And then I just take and I divide by 2, and that will give me 50 grams. So this is just a way to set up a chart to help you figure something out. I will teach you mathematically how to do it also, but this always works. A second half-life, I would just add 10 years, so now I'm at 20 years. So another half-life went by, and then I divide this in half again. So now I have 25 grams, and it wants 30 years, so I'm going to have 3 half-lives go by. So I'll have 30 years, I'll have 12.5 grams as my final answer. So this is a way just to set it up so that you're doing it right. Again, remember your starting line. Mathematically, you can figure this out by taking your original sample and multiplying it by 1/2 raised to the number of half-lives. So to find the number of half-lives, you're going to take the total years, so 30 years, and you'll divide by the half-life. So 10 years is equal to 1 half-life. So there's my conversion factor. I'm going to have 3 half-lives. So I have 100 grams times 1/2 raised to the 3. And so this is going to be 1/2 times 1/2 times 1/2, or 1/8. And then I just take that 100 grams times 1/8, and then that will help me find my sample. So it's just another way to think about it to do more mathematically, but of course the chart will always work. So don't ever be afraid to set up a chart when it's talking about half-lives. So let's look at this one. How long it will take for element X to decompose to 25% of its original value if it has a half-life of 2 days. So you can make a chart. So I'm just going to do half-life, time and amount. Again, start at 0, and I have 100%. 1 half-life goes by, that's 50%. 2 half-lives go by, that's 25%. And it says how long will it take? So that would be 4 days. So that's one way to figure out this problem. Or you could use that half-life equation that's given to you on your AP data sheet. Remember, that's the very last equation. So this is how you set it up. So 1/2 equals the natural log of 2 divided by that rate law constant. And notice that the half-life here, that's where that natural log of 2 comes from. And on the AP data sheet, they already do that mathematically. And I actually know the time. This time right here is 2 days. So let me set this up, equals 2 days. So we can solve for K. And I get K is 0.3465. And it says if 25% is less, so it says 25% is left. So that means I take the natural log of 4. So I have t to the 1/4 is equal to the natural log of 4 over the k. And I know what the k is. The k is 0.3465. So I have 1.386 divided by 0.3465. And my time when 1/4 of it is left is 4 days. So just kind of another way to work around it. But that's how you would use that half-life equation. Let's do another half-life. So this says, what is the half-life of N2O5 if it decomposes with a rate constant of 5.7 times 10 to the minus 4 seconds to the minus 1? So I'm going to write my half-life formula and plug in what I know. And I go ahead and divide that through, and I get 1200 seconds. And just to make that number a little bit manageable, I can divide by 60 and I get 20 minutes. And here's another question. How do you know this decomposition is first order? And that refers back to the unit of K. So if K is equal to time to the minus 1, then you know it's a first order. So your unit of your rate law constant will always reveal what order reaction it is. And half-life is always a first order reaction. So the decomposition of ammonia to give nitrogen and hydrogen follows this rate law. So rate equals K times the concentration of ammonia. So we know this is first order because they wrote us a rate law. And it does give us the rate law constant right there. That's what K is. And it says, what is the half-life of this reaction? So I'm going to do the half-life formula and then plug in the numbers. And I get 30.1 seconds. And B, it says, how long does it take for the ammonia concentration to drop to 1/10 of its original value? So instead of having half-life equals the natural log of 2, this time I'm going to take the time for 1/2 of it to become products is going to be the natural log of 10. And that over K. And go ahead and take the natural log of 10 and put in that rate law. And I get 100 seconds. So some tips with half-life and how to solve those problems. Let's look at second order reactions. In second order reactions, the integrated rate law is right here. And again, you can find that on your data sheet. So it would be the third formula down. And our units for second order reactions for the rate law constant are always time to the molarity to the minus 1 times time to the minus 1. And on this one, you get your straight line if you take 1 over the concentration with time on your x-axis. So you can look for that straight line. The curved lines would be concentration versus time, or the natural log of the concentration versus time. So second order reaction, and then notice that this is a positive slope. So all the other ones have a negative slope. The second order reactions, they have a positive slope. So let's do a problem that's a second order reaction problem. And this one says the rate order constant is, and I can tell it's second order from the units. And it says if the initial concentration of the HI in the container, so I know that initial concentration is given to me. How many minutes? So that's what I want to solve. So solve for T. And then I have my final concentration is given to me. So I know I'm going to use that third equation. So let's go ahead and write it. And then let's plug in our numbers. And let's simplify things. And then we're going to divide each side by 1.6 times 10 to the minus 3. And we get T equals 1115,000 seconds. And that's kind of big, so I'm going to divide by 60. And I'm going to get 1900 minutes. But that is how you will find the time for a second order reaction. Let's do another problem. It says the rate law constant for the decomposition of N2O5 is 6.82 times 10 to the minus 3 seconds to negative 1. So I know just from that, this is a first order. It says suppose we start with, so there's my initial concentration. And it says we have a volume of 2 liters. So we actually have to figure out the concentration because they don't give it to us the molarity. So I know my initial concentration, I'm going to have to take the 0.0250 moles on top per liter. So I have to divide through. So kind of initial concentration, finding it out. And sometimes the AP board does this. Lately they haven't, but they have done this in the past, so you just don't know what they're going to ask. It says, what is the rate order? We already solved for that. It's first order. And it says, how many minutes will it take? So we need to solve for time. So I know I need to do the first order reactions. That would be the second formula on your data sheet. And then this is going to be my formula. Let me go ahead and just write that out. And I'm going to rearrange to solve for time. Let's go ahead and plug our numbers in. And then let's take the natural log of those numbers. Watch your negatives. And we get for our answer 134 seconds. And if I divide by 60, I would get 2.2 minutes, which is asked how many minutes will it take. So that is how you do that problem. So in summary of kinetics of zero order, first order, and second order reactions, we have a sample rate law for each of the orders, 0, 1, 2. You should never have a 3 other than just identifying that you have a third order reaction by looking at the exponents and adding them up. You can use that integrated law equation or the concentration time equation and follow the order that's on your AP data sheet. So these should be in order 0, 1, and 2. And then your half-life equation is the very, very last one on that data sheet. So how can you tell which reaction you have? So they'll either tell you that it's a 0, 1, or 2 order reaction. They'll give you experimental data. They might give you a graph, and you'll want to look for the straight line. And so have that memorized, what straight line goes with what reaction. Or they could give you the units of your rate log constant, your K. You can use a graphing calculator to figure all this out. If you're interested in using your graphing calculator, this is a step-by-step how to use it. So if you'll follow the instructions, starting right here, so you can clear out the data that you have in there. You actually can have it calculate the natural log of your values once you stick them in, and also the 1 over the concentration. And these instructions will teach you how to do that. And you want to look for your correlation coefficient, and that is your R2. If it's close to 1, then that tells you that's the straight line graph. So having my calculator figure out all these concentrations for me just saves some time. But again, when you graph this out, you want to have that correlation coefficient, that R squared, close to 1. The one that's closest to 1, that tells you what order reaction that you have. And in this example that I gave you, this is a second order reaction. So you end up having the closest correlation coefficient closest to 1 will be the one where you're graphing the 1 over the concentration versus time.